Arijit does some really beautiful statistical physics. So I have long been trying to get him. One sec. So the title of the talk today is Ratcheting by Equilibrium Fluctuations, and Arijit Bhattacharyay is from Indian Institute of Science, Education and Research in Pune, in India. I'll briefly introduce Arijit. He was very modest. He didn't give me much details to go on, and I tried, but I've had not the kind of success that I could have had. Professor Bhattacharyay did his PhD with Professor J.K. Bhattacharjee from Indian Association for the Cultivation of Science in Kolkata. His PhD was on nonlinear dynamics of reaction diffusion systems. He next did 3 postdocs, one in Darmstadt, one in Padova, and one in Warwick in UK. And after these postdocs, he joined ISER Pune in 2008. One sec. So his research has spanned a number of interesting areas. He has worked on population dynamics, on protein folding, on one-dimensional superconductors, cell spreading, etc. And is currently an associate professor of physics and is also an associate dean of academics and graduate studies at ISER Pune. His present interests are in statistical mechanics of mesoscopic systems, micro-nano fluidics, Bose-Einstein condensate, and some aspects of gravity. So with that, let's welcome him. Arijit, you can get started. You want to put up your slides by using the share screen?
Yeah, thank you very much, Sohida, for the introduction and giving me this opportunity to talk. I have to share my screen now.
Just press the green button and then it'll ask you for which screen you want to share.
So I guess it's visible now. Okay.
Yes.
So let me go
totally
to the full screen. Okay.
Yes.
So I'm going to talk today about some equilibrium aspects of mesoscopic systems, small systems. Normally, it is believed at present, as all of us know, that there probably is not much left in the equilibrium theory of these things. Frontier is in the non-equilibrium domain. But I would try, in this talk, to motivate a few things where I would try to show that there are things, in relation with equilibrium of mesoscopic systems, where things are to be understood, in some more details. Particularly the area where there is a source of inhomogeneity of space, which does not show up in the Hamiltonian. Like for the systems where you have this diffusivity of a Brownian particle, which is coordinate dependent, or the damping, which is coordinate dependent, these are the things which actually do not go to the Hamiltonian. So those are not being present in the Hamiltonian is not going to show up in the Boltzmann distribution. So I'm going to show to you here a few interesting features that one can actually observe in systems where this kind of coordinate dependence of damping and diffusivities are there. Two things I'm going to discuss today. One is this ratchet. I would try to show you ratcheting, under equilibrium conditions, meaning you can actually get the directed motion of a structured object, not a single particle model, a structured object, symmetry broken structured object, that basically can move directionally into a heat bath under equilibrium conditions. And you can extract energy from this system. But of course, when you would be extracting energy from the system, that won't be equilibrium. But those same equilibrium fluctuations would actually get converted into the useful energy as you try to extract energy from the system in a weakly non-equilibrium manner. Okay, so the same fluctuations would basically work. So that would be one part that I would show. The other part that I would be showing here is that in the presence of coordinate dependent diffusivity of a Brownian particle, the equilibrium distribution, I would argue, that has to be a modified Boltzmann distribution. The reason being that the source of the inhomogeneity, that is this diffusivity or damping, those things do not really enter the Hamiltonian, and that is where one requires this equilibrium distribution to get changed. I would show you that it actually gets, I mean, it's very easy to get that because the standard theory basically gives that. Just Kramer-Small, expansion, the kind of Fokker-Planck you would get from there. If you do not do anything, go by Ito, you would get the distribution, equilibrium distribution, which is the modified Boltzmann distribution. Okay, so let's start with the flashing ratchet. In the context of flashing ratchet, what people believe is that you have to drive this system. You have to drive this system intermittently out of equilibrium to make the system move directionally. The drive is not directional, but you get a movement directional, and that is where the non-trivial thing is. And you basically extract energy from this kind of a system where the energy is contributed by that non-equilibrium drive, not the Bath fluctuations that much. Okay. So this is a nice schematic picture that I have actually got. Yes. Yes, Mahanti.
I think it's just that his mic may be unmuted. So no problem.
So,
go ahead.
Am I audible now?
Yeah, you're audible.
Okay.
Yeah.
So just look at the left panel of this. Oh God. What happened here? Yeah. So just have a look at this left panel. This is a flashing ratchet where you are not going to extract any energy from the system. What it shows you is that in the presence of this sawtooth potential, say the particle is staying here and it has a very small distribution because of this. This is confined by this steep potential and it basically experiences a temperature that gives a little spread. So this is the distribution of the particle here. Now, the moment you switch off this potential, this sawtooth potential, you basically come here and the particle's center basically remains here and its position distribution expands. So that happens when you switch off this, sawtooth potential. Now, again, you switch it on. As you switch on this potential, I mean, there was a probability for the particle to be here. So you get this little hump here. So the particle basically has moved from this position, from here to here, as you switched off this sawtooth potential and then switched it on. Okay? But you have not been able to extract any energy in this process. And the switching on and off of this, driving the system from equilibrium to non-equilibrium, this is a non-directional thing. But what has happened here is that you have basically got a directional motion of the particle. It has moved from here to there. Now, if you introduce another slope here and do the same things, switch it off, the particle has some probability to be here, and then switch it on. And then the particle being here, say, comes up here and then comes down here. And that way the particle has actually moved from here to there. There is some probability for the particle to move from here to there as you switch on and switch off, and then again switch on this sawtooth potential. So this is the ratcheting. Now, as the particle has moved here, under the action of this non-equilibrium drive, so the particle has actually got raised from this height to this height. So there is an energy gain of this much. But in that way, it had actually gone here and then has come down here. So this non-equilibrium drive basically had given this much energy to the particle, out of which a little the particle has actually gained. The rest is lost to the bath. Okay, so the efficiency of this system is this much little height divided by this big height times another fraction. That another fraction is basically this area, green area, divided by this whole area practically. because the particle had a probability when this thing was switched off to remain somewhere here, And if the particle were here, then when the potential is switched on again, it goes up here and comes back to its initial position. So that way the energy gets lost. Okay, so whatever energy this non-equilibrium drive had given to the particle, it has come back to its initial position, so that gets entirely lost. So that is where that fraction comes, multiplies the ratio of those energies I told you, and that fraction is this green area by this whole area, and that practically is very small. These two fractions give you, getting multiplied, give you a very small efficiency. So here the energy that is getting extracted from the system is actually given by this non-equilibrium drive. This, thermal Brownian motion, or this thermal, motion of the particle, that basically does some sort of a passive, that plays a passive role. So what I'm going to show you is a counter example of this kind of a thing. What I'm going to show you is that, under equilibrium for a structured object, just consider this middle panel. So under equilibrium for a structured object, if you have this kind of a distribution of a structured object's position of, the center of mass of the object, then you would be basically seeing that this thing would actually move, So when you are not extracting any energy from the system, it's equilibrium, then you would see that this basically is moving. And you can actually have, a slope like that, where you would be extracting energy from the system, that essentially would be a non-equilibrium situation. So there, from this motion, you can extract energy, okay? So the dynamics that I would be basically considering is the overdamped dynamics. Here in this kind of a situation where you are, which is weakly non-equilibrium, you are extracting energy from the system. What I'm going to consider is that the temperature remains constant, and the equilibrium fluctuation should basically, matter here in this weakly non-equilibrium situation. Temperature constant at larger time scales, so the system equilibrates very quickly, which is standard consideration. Okay, so let's go and see. The plan of the talk is that in the first part, I'm going to discuss these things. In the second part, as I told you, I would talk about those, equilibrium distribution of the system. So let's go to the model. And before going to that, let me just talk about this Feynman-ratchet, because often people I have seen say that, this Feynman-ratchet tells you cannot have, directed motion in equilibrium conditions, which is not correct. Feynman-ratchet indeed does not tell that. That's because the symmetry in the Feynman-ratchet is broken by temperature. And in equilibrium, when these two temperatures are the same, T1 and T2 are the same, there is no broken symmetry in Feynman-ratchet, and that is why there is no motion. Okay, as Feynman had shown this thing that, say, when this ratchet is being driven by this T1, it can actually move in a counterclockwise direction. Being driven by T2, it moves in a clockwise direction, and the probabilities are these two. And these two become the same when T1 is equal to T2. So the Feynman-ratchet, which is basically the Lippmann's ratchet, has a symmetry broken by temperature. In equilibrium, there is no broken symmetry, so no question arises, of having any directed motion here. But it essentially does not tell you that there cannot be a broken symmetry under equilibrium conditions. So it cannot deny that you can have directed motion under equilibrium conditions. So how would you be having? What should be the model? The model should be the simplest one: two spheres like that, a big one and a small one, and consider that there is some sort of a attractive interaction between these two. So this is the equilibrium position of these two spheres. They basically collide with each other, like hard spheres. And when they are at a distance apart, they attract each other, and this is the equilibrium position. Now, the Bhatt degrees of freedom would actually make these two spheres go to various distances, go away from its equilibrium position. And this process, when this drive, when it basically changes its configuration, being driven by the Bath degrees of freedom, that process is not going to give any directional translation, any translation to the center of the system, center of mass of the system. That's because the Bath is a homogeneous and isotropic. Okay, so when this thing, when these two spheres go apart, being driven by Bath degrees of freedom, if you consider the entire set of this thing and do an average over that, you are not going to get any transport of the center of the system. Now think of the response. Say these two spheres are at a distance apart, which was created by the drive by the Bath degrees of freedom. And now, as they're coming back, this bigger one is sluggish because it's losing more momentum. It has a bigger Stokes radius, so it's sluggish. And this one, comes much more faster because it's losing lesser momentum. Okay, so in that way, at the time of the response, this system would have a motion of its center of mass from the in a direction from this smaller sphere towards the bigger sphere. So that's the physics. So let's look at the maths a bit. So what I have done here is that I have written down, I have considered the center of mass of the smaller sphere to be x1, that of the bigger sphere to be x2, and I have written down the equation of motion of these two, where I have basically considered the damping of this particle x1, the smaller one, to be 1 minus beta, and that of x2, the bigger one, to be 1, where beta is a fraction that makes this damping constant smaller, okay, for the particle x1. Now, on the left-hand side, I have taken this, okay, I have considered the mass to be 1, this inertial part, and this force is basically the hardcore repulsion that I had told you that I'm considering for the sake of simplicity at the moment. So these are the faster processes, and on the right-hand side, I have kept the terms which basically correspond to the slower process. Okay, and this is the force. I'm considering a harmonic interaction between these two spheres. So that basically gives you this kind of a linear force. Okay. Now under overdamped conditions, this right-hand sides are basically 0. That basically makes the left-hand sides also separately 0. So I'm interested in this part now, because this part is not going to give you any motion of the center of mass. So this part, if we just look at this part, we get these equations of motion. I have taken this 1 minus beta just downstairs here. And you see that for the smaller particle, now this spring constant that has got renormalized. It's being divided by a smaller number. So this is a bigger number than alpha. So that basically makes this particle x1c effectively a steeper potential than what this x2 particle sees. Then what the bigger sphere sees is this one. So that's just because the bigger sphere loses more momentum compared to the smaller one. So at a particular distance, now the smaller sphere basically sees a bigger force compared to the bigger one, and that gives to the system an effective force by this breaking of the internal symmetry of the forces by the damping of the system. Okay, and for the system to equilibrate, that force that has got now generated has to be balanced. Otherwise, the system cannot equilibrate. And for that, the system would start moving. The overall damping force on the system would actually balance this force. Okay, and that would give you this velocity selection. For beta equal to 0, when there is no broken symmetry, I mean the velocity is 0. But there is a little subtlety. Let me talk about that. So here, what I have considered is that I have only considered the attractive part of the potential and not the repulsive part. I have just pushed that aside, considering that to be a hardcore collision. Okay, that's a very fast process. This damping is not defined there. So I just neglected that part. What if that is not a hardcore collision? If that is a soft collision, so there is some sort of a slope. And you use the same sort of, damping constants for the particles throughout, for the attractive and the repulsive forces as well. So in that case, the way the attractive part for the smaller particle has got renormalized, the repulsive part would also get renormalized, and you would see that you are not going to get any directed motion. So one has to win, either the attractive part or the repulsive part of these forces, that has to win. And for that, this damping during this attractive interaction, when particles are a distance apart coming closer to each other, and when the particles are touching each other, or the spheres are touching each other and repelling each other, at that time the damping, these two have to be different. And that, I mean, it's not difficult to imagine that they could be different, because these dampings basically, these things depend on the exposure to the Bath degrees of freedom. When these spheres are in contact with each other, then the accessible surface area to Bath degrees of freedom is much less compared to when they are at a distance apart. So the damping that basically renormalizes the internal force, that could be different at the time of collision, that is when the repulsive force is in action, compared to that when the attractive force is there. The moment those are different, you are going to get, again, even in the presence of the soft core collision, you are going to get a directed motion in this kind of a system. Okay, so here is a simulation. I mean, the simulation is very easy. I mean, just numerically integrate those two equations. But at times, this x1 can cross x2. Okay, and since these are overdamped dynamics I'm considering, there is no concept of mass, meaning that there is no differentiation of particles in terms of mass, meaning that you can imagine the mass of these two particles to be the same. And keeping in mind that you are employing elastic hardcore collision, means that when the particles are basically crossing each other, just exchange their positions, because there has been a momentum exchange when they had collided. Okay, so just keeping that in mind, one can simulate this thing, and one can see a very good match between between the theory and what comes out from the statistics that you would be getting by from the time series of x1 and x2, just by evolving these equations. So the distribution that you would be getting here is something like that. This Gaussian part is because of this harmonic attractive interaction. This sharp fall is because of this hardcore collision. Now, while trying to find out this average velocity of the center of mass, you should make sure to integrate over this part only, the attractive part only. Don't take into account the repulsive part. If you do that, you would get a 0. Because the repulsive part does not really, contribute to the motion of the center of mass of the system. Okay, so now this is the equilibrium situation where I cannot extract any energy from the system, but there is a directed motion. Okay, this is the equilibrium situation where the time reversal symmetry is broken. But anyway, you are on an inertial frame which is moving uniformly. And through a system where there is on average no force, meaning there is no entropy production. You have a current, but flux times force being the entropy production rate. Since there is there is no force present but only flux, there is no entropy production. One can legitimately call this to be an equilibrium situation. Okay, so let me quickly go to this energy extraction part, which I had done work with my student Mayank Sharma. Mayank is doing his PhD with me. The work is published here in Physica Scripta. So what do you do here to extract energy? You basically introduce that slope, this force. You basically introduce here this if, and now I have generalized the model where this V basically takes care of the attractive part of the interaction and the repulsive part of the interaction as well. I'm not really making use of this hardcore collision, which is something ideal. So here you can see that this Z minimum, that basically tells you Z is the distance between the particles. Z is basically x1 minus x2. Z minimum is the distance when particles are below that Z minimum. There is repulsion happening, so the collision process is happening then. And at that time, this mu is basically the damping constant. And when the particles are at a distance bigger than Z minimum, the Z is bigger than Z minimum, then this is the attractive part of the interaction that is playing there. And at that time, this gamma basically is the damping constant. As I had told you, that these two have to be different. If these two are the same, if gamma and mu, they are the same, then you are not going to get any directed motion. So these two have to be different, the damping constants at the time of collision and at the time of when the particles are attracting each other at a distance. And particle-wise also there has to be a symmetry broken. So that is why there is this 1 and 2, these indices. Okay, now if you can, one can just simulate this thing, and the velocity that also for this kind of a harmonic interaction, where below Z minimum this is repulsive and above Z minimum this basically is attractive. One can get the velocity like this, where the average velocity of the center of mass, this part is due to the presence of this force, the particle is just rolling down the slope. This part is that part, and this part is because of the mechanism I told you. And here you can see when this gamma 1 is the same as gamma 2, so this part is 0, so there is no broken symmetry, so this part is 0. Okay, the particle would only roll down under the action of this force F. Now keeping this force F 0, one can look at the equilibrium situation, and there this is something what we're showing here, where this F is basically 0. If there is a broken symmetry, you would be getting this kind of trajectory. If you make this, gamma I is the same, that is gamma 1 is equal to gamma 2, mu 1 is equal to mu 2, you won't be getting any directed motion. You would be getting this kind of a, trajectory. I mean, time series for the center of mass of the system. You can switch on the force F, I mean, against which the part now the system has to move, and there you would be getting, the velocity can be plotted, against all the parameters, the temperature, alpha, this gamma, mu. So where the velocity is basically 0, that basically means where the velocity due to the rolling down along the potential slope is the same as rolling up of the system. So this is some kind of a stall force that basically makes the particle static, and you'd get that stall force everywhere. So upward here, the particle is basically moving under the action of the force against which it was supposed to move, and below here the particle is basically driving against the force. So so what the point that I wanted to make here is that it's possible to have directed motion under equilibrium conditions. I mean, equilibrium fluctuations can make something move directionally, but this structure matters. One has to take into account the structure of the system and the broken symmetry properly. A single particle model is not going to show you that. A single particle model is not going to show you, give you any idea of the possibility of such a thing happening. So that I would like to move to the next part of my talk. So is there any question that you'd like to ask from the first part?
Yeah, actually, could you comment on what might happen with, say, double Weller and harmonic potential? instead of the harmonic potential that you've considered? That's question one.
Yeah,
And the second one is, what about correlated noise? I mean, do you think the nature of the noise has an effect on this?
yeah, nature of noise would have definitely effect on this. See, what the model I have shown you is an Inchua, okay? And this Inchua model has been used by a lot of people before I did this work.
Okay.
But everywhere, even Sriram and all, and they have done work on that. Everywhere they have introduced some sort of a, non-equilibrium part of the noise, okay? And under the action of those, they have seen, they have characterized the system, its motion and all. So those things are done. What I try to, stress here is that, I mean, those parts are not needed. If it is just equilibrium, situation, just white noise, it would work. And about the force, I mean, it doesn't matter. It has to be some sort of an attractive force. Okay, the details, it does not really matter.
Thank you.
Okay, so let me go to the second part where I'm going to discuss about the equilibrium of a Brownian particle, which is experiencing some coordinate dependent diffusion, coordinate dependent damping and diffusion. This part of the work I have done with Rohan. Rohan is an undergrad here, a very smart kid. When he was in his third year undergrad, he actually did this work with me. Okay, so let's go into that. What's the motivation? The motivation, as I have told you already, that I have a situation at hand where the space over which the particle is moving is inhomogeneous, even in the absence of any conservative force, meaning even in the absence of in the presence of a very flat potential. But 2 points over that space are different because the diffusivity or the damping, those are different at those 2 points. Now, if I consider the Brownian particle to be in equilibrium in this kind of a system, and if I go by Boltzmann distribution when U is 0 gives me a flat profile. So it does not really reflect the inhomogeneity of the space. And that tells me it's most likely that in equilibrium, this is the space, place where the Boltzmann distribution has to get modified. Okay. Now, to look for a modification of Boltzmann distribution, the crucial thing is this Fick's law. What one has to look at is what's the structure of the Fick's law when this, diffusivity is coordinate dependent. So let's have a look at that. So this is the Kramer-Small expansion. This is very standard, textbook thing. We all go by that. And the second Kramer-Small coefficient for this n equal to 2, that gives us this diffusivity. This d2x basically becomes a d of x if I consider my Langevin to be of this structure. Okay. And on top of that, if I consider that the Stokes-Einstein relation basically is valid locally, then this is also there. Now, this term, I mean, there will be 2 current terms, right? I mean, this has infinitely many terms on the right-hand side. This equation basically accounts for the conservation of the probability of the particle. And out of these infinitely many terms on the right-hand side, we must take either 1 or 2 or all the terms. That basically Paola's theorem tells us. I mean, to keep this transition probability positive definite, we have to do that. When we keep up to 2 terms, we normally call that equation to be the Fokker-Planck equation. And given this thing, this identification, this being your Langevin, I mean, from here, from the diffusive current part of this Fokker-Planck, you would get to see that the diffusion current is going to come out to be this. The moment this d2xt is you identify as dx, then your diffusion current density is this. Okay. So that is your Fick's law. When dx is a constant, normally in the Fick's law, this dx comes outside. But when the dx is coordinate dependent, Kramer-Small expansion tells us that this has to be the case. And this is the case which is any convention independent. You take any convention, you go by Ito, you take Stratonovich, you take any other convention Stratonovich like, it is always this, because this term does not depend on any convention. Only the drift term that depends on conventions. So let us have a better look at this term, why it is like this. Your diffusivity is by definition this. Now what I'm interested in is a local diffusivity, d at x. So I would relax this condition, t going to infinity. So this is diffusivity. Let me imagine there exists, a coordinate dependent diffusive space like this, where at this position x, diffusivity is dx, density is rho x. Here at x plus delta x, this is dx plus delta x, rho x plus delta x. And this is roughly the diffusivity and density over a length scale delta x here. And this is that over a length scale delta x here. Given that this current J plus, which is because of this part, moving from left to right, that is this, where this is the velocity. This is my diffusivity and my available length scale is delta x. Diffusivity divided by that length gives me the velocity, characteristic velocity of the system times this. This is J plus. Similarly, the J minus from right to left, this current because of this is going to be this. So the total current here at the center is J is equal to J plus minus J minus is this, where I have just done a Taylor expansion of this thing. And here I have got terms order delta x and higher orders in delta x. Now take the limit delta x going to 0 because it's a local diffusivity. That basically gives you this thing, which you have actually seen from the Kramer-Small expansion. So if this is the Fick's law for this kind of a system, then in the absence of a potential, some sort of say confinement, but the potential is flat in the middle, there, what kind of a probability distribution do you expect? In equilibrium. In equilibrium, there should not be any current. So that tells you your dx rho x has to be a constant. So that tells you rho x is c over dx, where c is a constant for a flat potential. Okay, where diffusivity is coordinate dependent. If Stokes-Einstein relation is valid, fluctuation relation, fluctuation dissipation relation is there, then you are going to get px written in terms of gamma x in this way. Now straightforwardly you can extend this thing in the presence of a potential ux like this, where when this u is 0, you get back your this expression, where your f of dx basically is the c over dx. So this is the probability distribution in the presence of a coordinate dependent diffusivity. Okay, and this is exactly what you get if you go by Ito. This is the dynamics. This is the Fokker-Planck that you would be getting if you follow Ito convention, which is standardly followed by almost every mathematician in this kind of conditions, equilibrium conditions. And in equilibrium, you have to set this current density to 0. In non-equilibrium situation, steady state, you normally set the divergence to be 0. Here, just by setting this thing to 0, you are going to get your probability distribution to be this, which in the presence of the local holding of the Stokes-Einstein relation, that is dx prime gamma x prime being kt, is this, which I had shown you. Okay. Now look at one thing. Take an average of each term here. So average of x dot is equal to average of this term and average of this term. Under Ito convention, this is 0. That's because this d of x depends on eta for all the times before t. That is where these two things are uncorrelated. Under Ito conditions, this is 0. So that requires for the system to have a stationary probability distribution when it's confined under some potential. I mean, that requires this has to be identically 0 for any f of x. And that indeed is identically 0, because when you take this, calculate this average, what do? You multiply this thing by this and then integrate, right? This dx and gamma x, they combine, and that basically means that you are taking a derivative of this term. So you can write this thing, if I consider this to be this p of x, so this is, so this you can write like this, where this p of x basically is this part, and this is a confined distribution, so the distribution is 0 at the two ends. So this integration is 0 to 0. It's going to be identical to 0 for any f. So that is where this Ito convention is so satisfying. If you do not take Ito, if you take Stratonovich or something else, then this is not 0. This term is not going to 0, because that basically results in, those are anticipating conventions. I'm going to go into details in a while. In that case, this term is not 0. Okay, and as you can see that had you used here, instead of this distribution, had you used just the Boltzmann distribution, that is, this term was not present here, only this part was there, then this thing is not going to identically vanish. You are not going to get this thing to be 0, right? The Boltzmann would not give this thing identically 0, but this modified Boltzmann gives that. Now, what normally people do here, the standard practice is that they use Stratonovich or Stratonovich-like things, generate a current here, and use Boltzmann distribution, as the equilibrium distribution for the system. So that also gives here some sort of a current, and then these two things together become 0. So that is normally done. Okay, but what I would try to do is that I would try to convince you that that's a wrong way to deal with this kind of a system. The first reason is that, imagine when this f of x is 0. In that kind of a situation, the noise is going to give you a current, okay, which is very different from a thermal noise, which we normally consider, under which we normally consider, the equilibrium of a system. That problem is not there when you take into account Ito convention. Let's look into this Ito versus Stratonovich thing a little more. Ito is the limit of, a discrete random walk, right? Where the Stratonovich convention is basically, it's a limit of a correlated noise, because it's an anticipating process. What it does is that, you were evolving your system from time t to time t plus delta t. In the Stratonovich, you basically consider the strength of the noise to be dependent on the strength of the noise at time t, and that at time t plus delta t, an average of these two. Okay, so that requires you to anticipate what's the strength of the noise at time t plus delta t, and that brings in this correlation. And in the presence of that correlation, it's very difficult to imagine that any equilibrium would be attained. But people normally use that as a mathematical trick. So if you go by Stratonovich, a generalized Stratonovich, you can write down basically, its equivalent Ito SD in this way, where this is basically the term which gives you drift, your force term. This is the term, this WT is a Wiener process. This is your stochastic term. And here you get an extra term involving the derivative of this force strength, which basically comes because of the correlation that is getting generated due to adopting this Stratonovich process or Stratonovich-like processes. In Stratonovich, this alpha is basically half. There is another interesting process that people normally use to get Boltzmann distribution, where they basically make this alpha to be 1. This is called some sort of an anti-Ito or isothermal process. What that does is that the moment you take this to be 1, that would basically, now as I had told you, the Fick's law has become del x of dx times rho x. So there is an extra term which is rho x times del x of dx. So that extra diffusion current term gets basically cancelled by this term. In the presence of that extra diffusion current term, you are never going to get Boltzmann distribution. So in the anti-Ito, when this alpha is 1, they actually cancel this term, and that way they get Boltzmann distribution for equilibrium. But the problem here is that your time evolution of the system at time t, from time t to t plus delta t, entirely depends on the noise strength, which would be at time t plus delta t. Okay, so that's something problematic. Some people had claimed that experimentally it has been seen. I mean, this is the paper by Wolf et al. And you know, there are criticism also. This Manila and McClintock, this PRL, this is basically, you know, a critic against you know, the result of this paper, and details you can find here, which is quite convincing that this kind of a process, you know, is something pretty close to impossible. Anyway, so why do people, to get a Boltzmann distribution as equilibrium distribution, why do people adopt Stratonovich or Stratonovich-like you know, conventions in the place of Ito? So when you consider basically an Ito process, what happens is that your diffusion is basically isotropic. Okay, the diffusion depends on the point where you are sitting. So the jump that the system would basically make, so this is your profile of your dx, the jump the system would make towards right and towards left, these two are the same. And the jump here the system, the particle would make towards right and towards left are the same. But this force strength, stochastic force strength, that basically depends on this d of x. D of x is smaller here, so the jump size is smaller. So there is local isotropy, but this breakdown of isotropy happens, you know, at a larger scale because of this dx gradient. So the jump size is bigger here because dx is bigger, and here the jump size is smaller. So this gives rise to this current, this extra part of the current in the Fick's law. Okay, and in the presence of this current, you know, you are never going to get Boltzmann distribution. You would always have that, you know, 1 over dx dependent amplitude of that. This is exactly where people adopt Stratonovich process. In the Stratonovich process or Stratonovich convention, the jump here to when it's going to happen towards right, since it's anticipating, it depends on the diffusivity on the right hand side of a point on the right hand side, which is obviously bigger. So when the particle jumps on the right, it actually jumps a bigger distance compared to the particle when it jumps towards the left, you know, towards left from this point, because towards left this dx is smaller, and the jump towards left here depends on where it comes. It's anticipating. So you see a local, you know, isotropy breaking here the moment you adopt Stratonovich or Stratonovich-like processes, unlike this Ito. And this basically gives rise to an extra current because of this local isotropy breaking. And that extra current people normally use to balance this one, to counter this current. And that way, you know, you come to get a Boltzmann distribution even in the presence of, you know, a coordinate dependent damping. Okay, what I'm going to show here entirely depends on Ito, so I'm going by this process. If you go by Ito, your distribution is this. Your distribution is basically this. So there is this 1 over dx amplitude, and you consider a barrier overcoming process, that is your system was here, you know, under you know, you are keeping some sort of a constant population density here. You are interested in the current here. I mean, the barrier, this is a barrier overcoming process over a given time, how many particles are going, you know, over this barrier, and that divided by the time on average gives you this current density. And if you use this modified Boltzmann distribution, you would be getting this current density. You use Boltzmann, you would get this current density. Now, what's the difference between these two? Difference is in this sign. You see here, the sign being negative, here the dx that would dominate this process is the dx which is here, you know, at the bottom of the potential, where this weight is bigger. Compared to that, here, when you employ Boltzmann, the dx that would dominate this process, this current, is the one which is here at the top of the barrier. But the particle spends actually a very short time over the barrier when it goes over this barrier. So this is a very fast process. It's very, I mean, intuitively difficult to imagine that the diffusivity here would actually dominate the process than the diffusivity here, which is correctly, you know, captured by this. Now, E2 being, you know, a continuum limit of random process, I can tell you that okay, this is the paper. Since I don't have much time now, let me just quickly tell you. You can actually have a simulation of a random walker where you can create a coordinate dependent diffusion, that is a diffusivity which differs point to point, but the system actually sees a uniform temperature, and that way the Stokes-Einstein relation is valid. To do that, what you would be doing here is that you would actually employ a sticking time to each point, and you make this sticking time PS to be coordinate dependent. In that way, you would make the moving probability PM to be coordinate dependent, and in that way you would make this D, the diffusivity, which basically just PM by 2, because there is local isotropy. PM being the moving probability, the particle can sit at a point, with this probability PS. 1 minus PS is the probability for the particle to move. To move right or left is equal. The isotropy is there locally, and that basically would give you this D to be PM by 2. Now you can make this P a function of X by making this PS a function of X position, and that way you would be having a coordinate dependent diffusivity. Now bring in the force. Bring in the force by breaking the isotropy in this way. This is basically your drift velocity, and if you change the probability of moving the particle, the probability of moving against the force for the particle by keeping a minus sign here, for moving, in the direction of the force, it would be positive. In this way, you can basically find, you can introduce the force where this twice kT, that becomes this n0. So in that way, just by this parameter n0, you can actually in this simulation keep a global temperature constant where your diffusivity is coordinate dependent. So this is exactly that, Stokes-Einstein relation holding locally everywhere under a constant temperature. So one can talk of equilibrium here in the presence of coordinate dependent diffusivity. So simulate this thing, you are going to get the probability distribution for this kind of a confining potential like this, where this asymmetry is because of that 1 over dx term. And you can see actually, a very good match between your simulated result and the analytic one. And then you can simulate these currents, these J0 and J0 prime, where J0 is due to the modified Boltzmann and J0 prime is because of the Boltzmann. And you can see that this kind of a process basically corresponds to the modified Boltzmann distribution, or not the Boltzmann distribution. So E2 process being, an uncorrelated, being something where an uncorrelated stochastic noise is there, can actually represent a thermal process, even where the diffusivity is coordinate dependent. And it shows us that there is probably existing a need to think of modifying Boltzmann distribution for the equilibrium of this kind of systems where the diffusivity is coordinate dependent. Thank you.
Thank you, Arijit. That was a Very interesting talk. The floor is open for questions, so I welcome discussions and questions.
Okay, so I have a question.
Yeah,
Uh,
Yes.
there are several examples, if you look at turbulence or Salis processes or financial market analysis, where these random walks have distributions that are not Gaussian distributions.
Yes.
But there's one thing additional that they scale in time, not necessarily a square root, but it might be different powers.
Right.
Uh, can can your theory be modified to give scaling for the distributions?
Yeah, actually, what I was trying to show here um, is a process which is undergoing some sort of thermal fluctuations.
Right.
Okay.
Hmm.
Now you can bring in, many different correlations into the noise, and that way, accordingly, things would change. But here, when I'm talking of equilibrium, I'm thinking of a system which is in a thermal heat bath, and even being there, it is experiencing some sort of coordinate dependent diffusion. This kind of situations you arise basically, when you consider a Brownian particle near a wall.
Right.
You see that the diffusivity of the particle basically changes as a function of the distance from the wall. Now, in a similar note, if you can think of a complex molecule, say a protein, in a cell, I mean, uh, under various configurations of this protein, this, uh, I mean, I would say the number of other residues screening a particular residue in that protein, that can change. Okay, in various configurations of that folded configuration of that protein, it would be, a particular residue would have many different number of neighbors. In that kind of a situation, you can imagine that the diffusivity of that particular residue could be dependent on, what's the configuration of the protein. Okay.
I see.
So the diffusivity, if you can think of the system undergoing, some sort of a Brownian motion over its configuration space, uh, you can imagine this diffusion to be configuration coordinate dependent. So these type of things people are considering these days in crowded, atmospheres where you consider such a mesoscopic system. But the noise is basically a thermal noise. Okay,
Right.
so it's devoid of correlations introduced by uh, hydrodynamics or those things.
Okay. Yeah.
But I cannot deny that there could be correlations, because the thing I told you about this Brownian particle near a wall, uh, I mean, this diffusivity variation that appears there, that's because of hydrodynamics. And in that case, that may introduce some correlation. And maybe the Ito is not the right process for this kind of things.
So the time scaling would only happen. So if what I understand you saying is that in a thermal equilibrium, you cannot have time-dependent distribution, scaling and distribution functions.
Yeah, obviously you
Like,
cannot.
yeah, I guess you cannot. Okay, thank you.
other questions?
Okay, I wanted to ask a question.
Yeah, Deepak, go ahead.
So, you have given some equations. If you postulate these equations, they have some kind of a solution. But is it reasonable to say that if you put a system in some kind of funny environment, which is different in different places, then eta will have to, the viscosity will have to behave this way, the diffusion constant will be this way. If it is attractive, then it has to be this, otherwise there is this beta. Is there a justification for these kinds of modeling? That's all.
Yeah, the obvious justification is I need to break the symmetry, and that symmetry I need to break by damping because
Mhm.
not by temperature, because in equilibrium I cannot think of a broken symmetry using temperature, which was there in this. So that is where I have. So why does it not make sense?
No, I'm
I
not
think
saying it doesn't make sense. I was just wondering if such equations of evolution can be realized in real physical systems.
no, in real physical system, the first part what I have shown
Hmm.
there, it was an ideal situation where I
Hmm.
basically considered this hardcore repulsion and this 1 minus beta and 1.
Hmm.
Second part where I generalized this thing, there I had just considered this mu i's and gamma i's. So those could be any function of space, right?
No,
So
in the
this,
model they can be, but I was just wondering if these kinds of systems can be realized in real experiments. That's
yes, I mean, it's a lot
they
of
have
people
been
are doing
seen.
experiments. I mean, Deepak, there is this 93 paper by Lipscheber and Pasho. I mean, where they have actually shown these damping and diffusivities to be, distance dependent from confining wall. And following that, there are many such papers. I mean, where experimentally people are actually seeing this
Okay,
thing.
thank you.
Any further questions? Please ask. Discussions are wonderful. That makes this more understandable. I do have a naive question, though, Arijit. One of the thoughts I was having is, what if you consider the same problem purely in the context of a microcanonical ensemble, as opposed to a canonical ensemble? So now your temperature itself becomes a fluctuating quantity, and you give it some form of variation. Can you carry over much of this work? Because then the advantage you have is you're not necessarily stuck with the Boltzmann distribution in a microcanonical ensemble. The distribution changes, and so I was just coming from that angle to see if that's a line that's been pursued, or if that's a line that's at all of interest.
So, microcanonical, you mean you want to consider an isolated system? So, are you having in your mind that you are taking into account explicitly a few Bath degrees of freedom, some randomly moving things, and something which is your system, and then given some initial condition and some sort of confinement beyond which it doesn't talk, you let the system evolve, and then you try to see what happens. So is it the picture that you have in mind?
Yeah, I mean, there was work done in 1985 by Ford, Lewis, and O'Connell, I think, where they, or maybe Ford and Lewis, where they worked out a fully harmonic system rigorously in the context of I believe, a microcanonical ensemble, if I'm not mistaken. It's been a while since I looked at the paper. So one can probably just build on work like that exactly for the system that you described, which is an isolated system with, so it's an effective bath with a system inside, and then.
Yeah, I understand. So the thing is that, I mean, the moment you want to bring in this temperature in this kind of a system, what you do is that you integrate out your faster degrees of freedom, and then effectively take into account their presence through a temperature.
Right.
Now, if that is doable, then at some point, I mean, that would effectively look like a system in contact with a bath at a constant temperature, canonical one.
Okay.
If that point is reached, then this kind of analysis makes sense. Otherwise, this microcanonical system, one has to just look at the dynamics, very closely into the dynamics.
Yeah, I mean, one of the things that we don't address in statistical mechanics, perhaps quite as honestly as we would like, is what is the nature of the interaction between the bath and the system? because the nature of the interaction between the bath and the system is it's supposedly weak, but what the hell does weak mean? And you know,
A whole lot of approximations are there, those we do not really normally pay much attention to, but are very important when the system is small.
exactly.
But is something you are considering to be a huge one, but your system is not actually talking to this whole bath.
Yes.
So these ideas of homogeneity and all these things basically kind of break down, and
Yeah.
proper attention is needed, in this kind of cases.
I mean, one thing that happens is that if you have a bath, then you definitely get high frequency contaminants in the systems dynamics that will be coming from the bath due to coupling, and that will have an effect. And we studied this actually in the early 2000s with one of the students of Dave Kofke, who actually was in the audience from chemical engineering. And we did a couple of studies, and we found that there were some interesting effects that you could find. So yeah, so this is something to think about. Maybe there is something there where one can generalize this kind of treatment into the context of a microcanonical system with actual non-trivial or sort of non-trivial system bath coupling built in, and from there you can take out the limit of the canonical system that you talked about, but there may be other limits where it may be possible to incorporate descriptions of more biological systems and so on and so forth, if a framework can be constructed. Okay, I'll shut up. Any other questions?
I've got a question, if I may.
Yeah, super, go ahead.
So, could you please offer some insight onto how this spatial dependent diffusion might affect pattern formation, self-organization? In particular, given your background in reaction diffusion equations, I'm thinking about, so what happens at Turing instability if and that sort of phenomena, like self-organization, a pattern formation because of this space-dependent diffusion.
Yes, what would happen is that in your reaction diffusion system, that Laplacian term, that would change because now, the D has gone inside. So this is D Laplacian density, right? That's the diffusive current term. That would change now. The D would go inside. Okay, and as a result, there would be changes.
Right, so correspondingly equilibrium points might change, you have more stability. Okay, thank you.
Yes.
I want to mention that we have two interesting talks coming up in March. This is the last talk in February because we try to do it every other week. We have Doug Durian from UPenn, who is an experimentalist. So we don't get too many experimentalists to come. Doug has kindly agreed. So Doug is giving a talk on March 6th, I believe. And then we have an unusual talk by Roland, what's his name? Roland something. So Roland Geyer. Roland Geyer is from UC Santa Barbara. And Roland Geyer actually is a physicist who has gone to work on the problem of what to do with plastics that's really killing the world. And so this is going to be a somewhat slightly different kind of talk, but it'll be a physics-ish talk by a physicist who has gone to solve some really important problems. He's quite famous, actually. So he will be speaking towards the end of March. And then we have another lineup in April, which I think also would be of great interest. But I wanted to tell you guys, that Roland Geyer's talk would be a very different kind of talk. And I just wanted to, see if we could bring in a little bit beyond what we are doing in the statistical mechanics world to what's going on outside the statistical mechanics world, and how those problems are both important from a social and environmental context, and also from a scientific context, kind of bring it in, because that's one place where we often get siloed in. So it's a bit of an effort to stretch the silo. So I hope you will join us. And any other questions before we close? If you have any other questions, please feel free to ask Arijit. Okay, wonderful. Thank you so much, everybody. Thanks for joining in. It's been a great Saturday morning for us here, and thank you, Arijit, for sparing your evening and night. And
very much for giving the opportunity.
Oh, this has been a wonderful time in the morning, and so good to see so many of you. Thank you, and bye bye. I'll post the recording later today.
Thank you.
Bye.
Thank you. Bye.